Trigonometry, Chapter 6, Inverse Circular Functions and Trig Equations, Section 1, Inverse Circular Functions, Video 7, Rewriting Trig Expressions Algebraically. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous videos, we learned how to evaluate compositions of trig and inverse trig functions. Should be plural, but that's okay. In this video, we will learn how to rewrite such compositions of functions algebraically, meaning with no trig functions. This does happen quite a bit in calculus settings. For example, let's rewrite cosine of sine inverse of u over 2 algebraically in terms of u only, no trig functions. How do we do this? Well, essentially, we approach this the same way we approach such problems numerically. However, since there will be variables involved, possibly x and y, we will deviate from using the x, y, r definitions of trig functions and instead use SOHCAHTOA definitions. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent, and of course their reciprocals. Also, if no quadrant is implied, we use plus minus as necessary. That usually stems from taking the square root of something because we're using the Pythagorean theorem. All right, so first we're going to label the two sides of the given ratio in accordance with the SOHCAHTOA definition of the inverse trig function. Translation, this guy, well, just the sine, not the sine inverse. Interpret it in terms of SOHCAHTOA. Sine is opposite over hypotenuse. So we're going to assign opposite and hypotenuse to the top and bottom of that ratio. Opposite is u, hypotenuse is 2. Then we set up a ratio on the other side of the equal sign in accordance with the SOHCAHTOA definition of the final trig function, in this case cosine. Cosine is adjacent over hypotenuse. So on the other side of the equal sign, we'll set up adjacent over hypotenuse. And now we got to find the missing piece. Notice we have assigned values for opposite and hypotenuse, but not adjacent. We have to find adjacent. We're going to use the Pythagorean theorem. So set up the Pythagorean theorem, adjacent squared plus opposite squared equals hypotenuse squared, substituting the representations that we've defined based on the first trig function. Opposite is u, hypotenuse is 2, and we get that. Now we start solving for adjacent. Square the 2 to get 4. Subtract the u squared to get 4 minus u squared, and then take the square root of both sides. Now, we don't have a specific quadrant. When you square root both sides of an equation, you use plus minus. But now we have a representation for the adjacent side. The hypotenuse was defined or represented by 2, so we just have to set up our ratio. Substitute hypotenuse equals 2 and adjacent equals plus or minus square root of 4 minus u squared, and we get our answer. We've written the expression completely algebraically with no trig functions whatsoever. This is a skill necessary for calculus students. Let's try another. Oh, summarize it. Cosine of sine inverse of u over 2 is plus or minus square root of 4 minus u squared over 2. If we knew more information, we could pick plus or minus, but for now, that will suffice. Let's try one more, but efficiently. We're going to, oh my gosh, what is this? We're going to rewrite cosecant of cotangent inverse of square root of 2u squared minus 1 over square root of 2u squared plus 1 algebraically. And yes, you encounter situations like this in calculus. So let's just go through our process. From the SOHCAHTOA definition of tangent, we get cotangent is adjacent over opposite. So we're going to assign the following. Adjacent is square root of 2u squared minus 1. Opposite is square root of 2u squared plus 1. Now, also from the SOHCAHTOA definition, we have cosecant is hypotenuse over opposite because it's a reciprocal of sine. So that's what we're going to set up, cosecant. But we need an expression for the hypotenuse. Here comes the Pythagorean theorem. Don't worry, it's not as bad as it seems. We're going to square the adjacent, square the opposite, add them. That's equal to the hypotenuse squared. But the squares cancel the square roots, leaving 2u squared minus 1 plus 2u squared plus 1. The ones cancel and the u squareds combine to get 4 of them. And now we just take the square root of both sides. Luckily, the left side is a perfect square. So when we square root it, we get 2u with the plus minus. So Cosecant of cotangent inverse of that fraction, cosecant is hypotenuse over opposite, which was 2u over the square root of 2u squared plus 1 with the plus minus in front. And if we rationalize the denominator, we get plus minus 2u times the square root of 2u squared plus 1 over 2u squared plus 1. Nothing cancels. The 2's don't cancel. The u's don't cancel because the 2u squared in the denominator is part of an addition problem, not eligible for canceling. So that one wasn't too bad. Now you try. Rewrite each expression algebraically. Sine of tangent inverse of 5 over the square root of x squared minus 25. And secant of cosecant inverse of x squared plus 1 over 2x. Give it a try. There's a little surprise on the last one. All right, here's your fair warning if you haven't paused the video. Solutions in 3, 2, and 1. For the first one, from tangent, which is opposite over adjacent, we get opposite is 5 and adjacent is the square root of x squared minus 25. If we use the Pythagorean theorem, we get the hypotenuse is plus or minus x. This is actually fairly easy to see. If we square the opposite side, we get 25. If we square root the adjacent, it cancels the square root. The 25's cancel, leaving hypotenuse squared equals x squared, square root both sides. So the outer trig function sine is opposite over hypotenuse, which is 5 over x with the plus minus in front. On the other one, there was a little trick that I built in. Let's go through it real quick. From cosecant, the reciprocal of sine, we get a hypotenuse is x squared plus 1 and opposite is 2x. From the Pythagorean theorem, we would end up getting adjacent equals plus or minus the square root of x to the fourth minus 2x squared plus 1. But here's where the built-in trick was. When you set up the Pythagorean theorem, the hypotenuse did get squared. And if you squared it properly, by writing it twice and then doing a FOIL problem, you should have gotten x to the fourth plus 2x squared plus 1. But then you eventually subtracted the square of 2x, which is 4x squared. So when you subtract 4x squared, you should have got x to the fourth minus 2x squared plus 1, which is where this part came from. But if you were really on top of your game, you would have recognized that since that was supposed to be a highlight. Let's see if we can erase that up. Can I undo that? I cannot. All right. So, well, that was very disappointing that I accidentally erased all that. So I'm going to do it one more time real fast. When you square the x squared plus 1 squared and subtract 2x squared, which is basically in solving the Pythagorean theorem, you get x to the fourth minus 2x squared plus 1. But in the process of doing this, when you FOILed out the x squared plus 1 squared, you got x to the fourth plus 2x squared plus 1. And hopefully, I want highlighter, please. No, I want highlighter. Hopefully, after squaring the first binomial and getting that, and when you saw this one, you were thinking, wait a minute, is that a perfect square also? It was. It was x squared minus 1 squared, which, of course, being under a square root cancels, giving us the best looking answer that you see here. So if you didn't catch the algebra move that the part under the square root when you were doing the Pythagorean theorem here was a perfect square and therefore canceled the square root, I understand, but at some level, you have to start looking deeper into problems and looking for trends and patterns that you can capitalize on. And that was specifically why I put that there.